All right, so this is for problem 2 on the ESE 403 final for Max Mazursky. So below we're going to start with problem 2, which says consider the following problem. Maximize z equals 3x1 plus x2 plus 4x3, subject to the constraints 6x1 plus 3x2 plus 5x3 is less than or equal to 25, and 3x1 plus 4x2 plus 5x3 is less than or equal to 20. And all of those values are positive. So first we're given the set of final equations. So up here in part A, we can see clearly from the equations that x4 and x5 are 0, given that they're not found in the objective function. So we wouldn't want to include any of those as they would just decrease the value of z. It wouldn't help us increase that at all. Similarly, when we're able to take those out, we are left with these equations. And as you can see, as x2 increases, the value of z will decrease. So obviously, it would only impact the constraints negatively. So we want to set those equal to 0. And you find that x1 is 5/3 and x3 is 3, giving us a maximum value of z equal to 17. In 2b, we're responsible for constructing the dual problem. So what we're going to do is I'm going to kind of compare the two equations. So first of all, we take the coefficients from the objective function and make those our constraints. So as you can see, the 3 finds its way down here, the 1, and then the 4. Similarly, we take the constraints from the primal problem, and those become our objective function. So we have 25y1 plus 20y2. Obviously, it's a dual problem, so we're minimizing. And then we take these coefficients and we transpose it, and then it becomes this final problem. So you have this 6x1 and 3x1. That becomes 6y1 plus 3y2, 3x2 plus 4y2, 5y1 plus 5y2, and obviously these are both non-negative values. So from there, we were able to construct this graph in order to identify the optimal solution, and to verify it, we built the graph. So we drew the lines of the various constraints, as you can see. And what you can see is that this is the feasible region because it's greater than. And then obviously the corner point feasible solutions that we're looking at are this one, and down here at 4/5 comma 0. So plugging in the values for 0 and 1 and 4/5 and 0, you get equal values of 20. And then finally finding out what this point is, we come down here, we see that it's 1/5 comma 3/5. And plugging that into the equation yields a value of 17, which is the minimum value. So it's proven that for under duality that this is the optimal solution. So then in part D, we change up the problem a little bit to maximize z equals 3x1 plus 3x2 plus 4x3, subject to constraints 6x1 plus 2x2 plus 5x3 is less than or equal to 25, and 3x1 plus 3x2 plus 5x3 is less than or equal to 20, and all of those variables are greater than or equal to 0. So what we did is we first constructed the dual in a similar way. So the coefficients to the objective function and the primal became our constraints, so 3, 3, and 4. And the constraint on the right-hand side of our primal problem became the variables 25y1 plus 20y2. And then we again took the transpose of the coefficients on the, as you can see right here, this part of the equation we transposed to become 6y1 plus 3y2, and so on and so forth. So the question asks us to see whether or not the previous optimal solution is optimal. And as you can see over here, that if we substitute in the value of 1/5 comma 3/5, we see that this actually violates that second constraint. 2 times 1/5 plus 3 times 3/5 is 11/5, which is not greater than 3. It's a little bit above 2. So we know our solution is no longer feasible, so therefore it's no longer optimal. Under the fundamental insight, we know that the coefficient of the original variables in rows 1 to m is equal to b inverse times a. So multiplying b inverse times a, we get negative 1/3 comma 4/5, which would be the new coefficients of x2. In part F, we know that by setting x2 to 0, and then we're taking the dual of the problem similarly to what we did before, we find that 1/5 and 3/5 actually still violates the constraint by the new constraint that's created. As you can see here, that 9/5 is not greater than or equal to 2. And again, in part G, we do a very similar thing here where we use the fundamental insight of b inverse times A equal to A star, and that equals 1/5 and 3/5, and that should be the new column.